Oh, wave motion, really short. Like, it's 2 days worth of stuff in our book. I'm going to try to stretch it out a few more days, and then you're going to have a quest on this on Thursday. Okay? Check the board. It's on the board. Yeah, 1 week, exactly. Oh, well, life goes on. Okay, here's some terminology. And by the way, for your energy test, you know that little piece of paper I gave you? Yeah, guess where I got it from? Right here. I got it color. Sorry? No. Keep it. All right, so wave properties. I don't have a jar filled with water, but let me show you this. That is Tacoma Narrows Bridge, built in 1940. I know it's color. They probably didn't have color then, but they enhanced it since. And what the heck's going on? Let me quote what they said when they built this bridge. This is a modern feat of engineering. This is the best bridge in the world. Tacoma, Washington. Yeah, people did actually drive it when it was doing this. They thought it was cool. They called it the Galloping Gertie Bridge. Hold that thought. So you see all the wires that connect the bridge deck to this main wire that goes up to the top? It was like this before, but this one was longer. Cable holding all the other ones, so that thing's probably like, 2 feet thick. This is what you call resonance frequency. They actually have a name for it. It's called Aeroelastic Flutter. Now, I don't know if they came up with that term because they noticed this happened, or if it's something that existed before. Professor Farquaad risks life for dog and cat. Well, hold that thought. Did you guys know asphalt is actually a fluid, like concrete? Well, do you see it breaking? It's a fluid. So this is what, some guy getting some dog? So why is it doing this? The wind is going through all these cables, causing them to vibrate like a big long wave. And they're all tripping a certain frequency. And so they elongate and shorten at the same rates. And this is what's happening with the bridge. So there's a nice 1939 car.
Notice it's not sliding down.
Ah, friction between the tires and the road. Yes, good observation, Calvin. And then uh-oh. No more good vibrations. How much was a bridge in 1940? 5 million? 10 million? I don't know. No, because they learned from this. Like I said, in 1940, this was the best they could do. Well, we've come a long way in 70 years. This thing lasted 6 months. As soon as they built it, it started doing this. And the engineers said, I think it's fine. Sure, drive on it. Yeah, let's go.
It wasn't supposed to do that?
No.
Oh, I thought it was.
Of course, you don't want a bridge to move up and down.
Well, I thought it was to make it like not get blown up right now.
No, it's just showing you with this very stronger wind that came this one day. was just a little too much for it to take. So yeah, nobody died. This particular good. Okay. Now we know a little bit more about the properties of some waves and what they can do if you do things wrong. Okay. So, those weren't good vibrations. Those were bad vibrations. Waves. There's lots of kinds of waves, not just the kind that you do at the stadium when you're watching a football game or a hockey game. Light is a wave. That's how we all see. It's one tiny part of the electromagnetic spectrum. This is the electromagnetic spectrum. We're going to see this later on, but it goes all the way from radio waves, low energy, huge wavelengths, like miles and miles long, to gamma rays, which is really short wavelengths, huge amounts of energy. What do we do with gamma rays? We kill cancer cells with them. We zap you with them, and it kills stuff. You want to kill the bad stuff, not the good stuff. The tiny little sliver from 400 to 700 nanometers is the part you can see. And that's a good thing. We were having this discussion the other day. You don't want to see all this other stuff, because it would be like walking through very thick pea soup all the time. If you could see all the cell phone waves, all the radio waves, microwaves, if you could see all this stuff, you wouldn't be able to see anything at all. So luckily, we only see this tiny little bit of electromagnetic spectrum we call light waves. There's sound waves. That's how you're hearing me right now. It's a sound wave. Radio wave. Earthquakes, water, shock. Yeah, brain, sure. All right? These are all waves. The periodic wave is the one we're kind of concerned about, and when you're taking Math 12, we analyze this in depth quite a bit. Okay, where does a wave come from? Here's the key word. What is the source of the wave? What makes it? Energy. Okay, if there's no energy, there is no wave. Doesn't really say it here, but there's two main types, and yes, this will be on the test. There is a mechanical waves. Okay, mechanical, it's like touchy-feely type stuff, right? Yeah, this requires a medium. This isn't about fortune telling. It's some substance for this wave to travel through. Water waves, well, obviously the medium is water. You're hearing a wave right now. What medium is it transferring through? Air. If there was no air here, would you be able to hear me? Yes, correct. Sound waves don't travel through space. There's no medium for them to travel through. Okay, so these require a medium to travel. So like, just a couple of examples, water and sound. These are different types of waves also. Okay, so mechanical, the other one is electromagnetic. Do those infrared rays come to Earth from the sun and warm us through some medium?
Can I hear what it is?
Huh? It's space, right? And what do we call that? What kind of energy is that? The sun heats our Earth by the form of radiation. Yeah, we just got that in our energy test, okay? So, first of all, so no medium required, okay? All these rays that hit us, go through us, whatever else. Infrared, that's part of the spectrum. X-rays, okay, that doesn't just mean we're looking at your bones. We get X-rays that are generated from stars millions of light years away. We can see them with those waves. Just because it's not visible doesn't mean we can't see them with a special camera that we fix to the Hubble telescope. Okay, light, of course. We see the sun. All these other forms, okay, radio. They also emit stars, radio waves, etc. Sorry? Well, not with the naked eye, no, but yes, we can see them if we adjust some special filters and things and put them on cameras. We can still see this stuff, yeah, you bet. So see is a relevant word. Okay, gamma, high energy stuff. Okay. Yeah, all right. Wavelength. That would mean the length of the wave. What unit do we want for a wavelength? Meters. Okay? It's the length of the wave. Wavelength. Don't get confused. It's a really, really easy word to understand. It's given a symbol called lambda. Greek letter. First one you got was pi. We'll see a few more before you get through this course. Okay, Greek letter lambda. This is actually in Science 8. Do you recall this stuff? Here's a wave. This is actually periodic motion. There's one cycle of it. From start, goes up, goes down, and it finishes. Here's another cycle. Here's another cycle. You see how it repeats? This is what we know as periodic motion. Okay, it's some repetition, some motion that repeats, some cycle that goes on and over and over again. Okay, so we have what's called a crest. That is the top. Amplitude is the distance between the top and its rest position. If this thing has no energy, think of it as, we always want to think of a water wave, because that's the most common thing we've observed that's similar to this. Okay, if the sea is calm, there's no waves, right? So that's like no energy. As soon as you put energy into this, the wind blows on the ocean, we start getting waves. Okay, it crests up, but we also have what's called a trough. And the amplitude is the same here. That's the same distance as this. Okay, we got crests, we got troughs. What is the wavelength of one wave? Well, I could take it from start to where this cycle ends, or I could take it from one crest to the next crest, or I could take it from one trough to the next trough. It's all the same distance. Okay? This is actually what's called a sine wave. A cosine wave would start here at the top, but let's not worry about that till we get to Math 12. Okay? That's about it. This is, you remember this from Science 8? Yeah. Okay, and if you got a really good memory, you can go back 3 years. Well, there'll be that much less to think about. Frequency. We've talked a little bit about frequency and period. Let's talk a little more about it. What's the relationship between frequency and period? There it is again. That's what we call what type of relationship? Inverse relationship. If you know the frequency, just divide it into 1, and that's the period. If you know the period, do the same thing. That's the frequency. It's an inverse relationship. Couple of examples. Okay. Guy's pedaling his bike. Okay? He can pedal really, really, really fast. The definition of frequency is a cycle per a unit of time, but all we really care about is seconds. We don't care about weeks or months or, like the woman cycles in months. We don't care about that. We care about cycles per second. Well, where do you think they get the word period from? Okay, so I can pedal this thing five times in a second. Okay, I'm pedaling pretty fast. What's my frequency of me pedaling? Yeah, good. Cycles per second. This time a cycle is a pedal. It's one revolution of the pedals. Well, if I do that 5 times in a second, that's 5 cycles per second. So my frequency is 5 cycles per second. But we have a word for 1 over seconds. It's hertz. Okay? 1 over second is a hertz. Because we don't want to say 5 over 1 second, 5 over seconds, 5 hertz. Okay? Named after Mr. Hertz. Good question. It's probably American. Yeah. Okay, why don't we want it in seconds? I don't know. It just works out to a nice number, right? 5,000 RPM. You know, most cars redline at about 6,000 or 7,000 RPM. Motorcycles redline at 13,000 RPM. Formula One cars top end limit, what's it now these days? Because they just changed the engines. Well, 18,000 RPM. They can go to 25.
Yeah, they can redline.
Yeah, that's a legal requirement. They're not allowed to go any faster. But that increases reliability as well, right? The more RPMs you get, you know, the faster you live, the shorter your life type thing. Anyway, that's the frequency. How do I get the period? It's 1 over the frequency, or 1 over 5, which is 0.2. Period is what? Time. What's the unit for period? What's 1 over a second? It's in seconds. So in layman's terms, let's say this again. He pedals 5 times a second, 5 cycles per second, that's 5 hertz. Period is the time for 1 cycle. How long does it take to pedal the pedals around once? 1 revolution. 1/5 of a second, or 0.2 seconds. That make sense? Because you do it 5 times in a second, for 1 period, it's 1/5 of a second. All right? Here's another example. Good old pendulum. This guy's going to swing all the way there, and then all the way back, and that takes 2 seconds. That's the length of time for 1 cycle. This time a cycle is a swing from start to finish, right? So that's its period, 2 seconds. What's the frequency? How many cycles does it do per second? In 1 second, it only does half of its swing, right? So that's its frequency. Half of a hertz, 0.5 hertz. Make sense? One's the inverse of the other. Got one more for you. Ooh, I forgot my box. Who knows what this is?
Oh, that's a frequency.
A frequency thing. A frequency thing. Huh. That is vibrating 256 times per second. That's what we call middle C note. What's the frequency of this thing? 256 vibrations per second. That's 256 hertz. Okay? I don't care what the period is. It's some stupid small number. How long does it take for 1 vibration? It's a really, really short period of time. So it's not really helpful. But anybody know if I double the frequency of this thing? First of all, what do I call frequency in music? Pitch. If I double this pitch, does anyone know what that would sound like? This is, okay, let me embarrass myself a sec, okay? Ha 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 ha. That is 1 octave. Double the frequency. Yes. This is 512 hertz, double 256. Is that an octave? It is, right? 1 octave higher. Okay. So twice the frequency is exactly 1 octave. That do, re, mi stuff that I tried to do. Okay, that's frequency and period. You're going to do that again. So, a dog's tail wags 50 times in 40 seconds. What's the frequency? What's the definition for frequency? Cycles per unit of time, but it's always going to be in seconds. So in this case, what am I talking about when I say a cycle? 1 wag of a tail. 50 wags in 40 seconds. What's 5 over 4? 1.25 hertz. That's how many wags per second. 1 1/4 wags. How do I get the period? Yeah, just take 1 over it, which would give you 0.8. What's the units for period? Yeah, this is 1 over seconds. If I go 1 over seconds, that's seconds. I'll leave you those to do. Oh, one other thing I was going to show you.
Is that what that is?
What? This?
The thing you were just hitting on.
That, yeah. Well, this is just a box to amplify the sound. Come on. Here we go. What's the relationship between frequency and wavelength? Here is the physics of music, notes. So middle C was what I just did. That was a frequency of 256. They got it off a little bit. Okay, there's just different ways you can tune things, I guess. I don't know. My music theory isn't that great. But C4, that's middle C. But notice as the frequency goes up, what happens to the length of the wave? It gets smaller, doesn't it? Is that what we call an inverse relationship? Here's all the notes. Yes, it is. Okay? So the next formula we're going to look at, let's just hop right there now, since I'm talking about it, is this guy. What does that thing say? We know what F is. Okay, we know what's lambda? It's a length, it's wavelength. And V is good old, what do we got for V? Yeah, that's velocity. What?
Is that how fast the waves are going?
Exactly. That's how fast the waves are going. Let's look at this. That is frequency times lambda. What's the units for frequency? Which is 1 over seconds. And what is this? Wavelength, which is in meters. Is that units for speed? It is. Meters a second, right? So that's a formula that will relate your frequency and your speed of a wave and the length of the wave. Okay? So as you can see, if I have the same speed, if that's frequency times wavelength, if the frequency goes up, then the wavelength must go down in order to equal the same speed. It's an inverse relationship between F and lambda. Okay? In words, that's what that says. So, let's look at this. what did I just say? If the waves maintain a constant speed, what happens to their wavelength if the frequency is doubled? If this is times 2, and this is a constant, it doesn't change, then this thing must, yeah. Okay? There's no numbers here. That's just knowledge of how formulas work. That's just math. If this is halved, then what happens? This one must be doubled for this to still equal 1, the same thing, right? Okay, so inverse relationship between frequency and lambda. I'll let you do these two. Couple other things, just going back to waves. There's two types. A transverse wave, which does this thing. If I pull this slinky, if I put a wave in it sideways, can you see this? Okay, it goes and continues. And I wish I had a really, really long one. But when I put in a side wave, it goes to the end, reflects back, and it continues to go sideways. The other type of wave I can put into this is exactly how you're hearing me right now. It's called a compression wave. So if I give it a pulse this way, you see how it reflects off the ends and comes back and forth? Okay? Now something with an earthquake actually does both. It's a little more complicated. It's mainly a compression wave, but after that happens, there's secondary waves that do this. Okay? That's why it does lots of damage. Okay? Okay, so transverse, that's A. Longitudinal is another word for a compression wave. Okay, transverse means across. Okay, longitudinal compression means if you just compress that in the same direction as the wave is traveling, then that's the type of wave it is. Okay, let's see what this is. What kind of wave is that? Transverse. You see how the particles are going right angles to the direction the energy is actually traveling through this wave? So that's how the surface of the ocean works. Okay, the energy is blowing from the wind, say from the left, and all that energy can come in the shore, and actually lately in the lower mainland, it's too much energy. And all these nice homes that are built right on the water because they love the ocean view are actually eroding. Even concrete walls are getting destroyed, like last few days down in Delta, if you watch the news. Too much energy. A little ducky sitting right here in the water, he just goes up and down and up and down, and all the energy just goes right underneath him to the end of the wave, right? So these particles, this is transverse. They move at right angles to the energy of the wave. Okay? So my hand goes that way, but the energy is actually traveling in that direction. Compression wave. Will look like that. Okay? Now, like I said, that's compression. That's how you're hearing my voice right now. All the particles of air, it's pushing up against and banging the next set and banging the next set until it vibrates stuff inside your eardrum, which makes a signal to your brain and goes blah, 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 blah. And if you understand the language, it actually makes sense. Okay? See that red dot? He gets hit with that, transfers his energy to the next one, and so on, and so on, and so on. And it happens, in this case, at the speed of sound, which is about 343 meters per second. Okay? Energy, same direction. Energy, right angles. Transverse compression. Okay, that's about it. So, page 176, 2 and 3, 178, 2 and 3, and then 181, 1, and 3 to 12.